So, hello and welcome to everybody. My name is Nikolay Angelov, and tonight I'm going to present to you some of the issues that we currently face in the blockchain ecosystem. I decided to do this talk because everybody in the world is talking how great blockchain is and how it will change the world, but in reality we are far away from this happening, and we currently face many issues that we need to overcome first before actually changing the world. Before I continue with the talk, I want to say that I have prepared a Slido for the online people. So if you're online and you want to ask me questions, you can use this tag here, and the people in the room can just raise hands. Okay, so let's do a quick overview of what I'm going to cover tonight. First off, I will start with very simple blockchain overview. I hope everybody here knows what blockchain is and how it works, but still we need to make a few points clear so everybody knows what I'm talking about later. Then we are going to jump on the first set of issues, that is the scalability problems. Then we are going to talk about smart contracts problems, and in the end, it is the fun part. We are going to travel to the future to see what the future has in store for us in terms of problems. So, blockchain overview. What is blockchain? Well, I hope everybody knows. Again, I hope everybody understands this picture, but pretty much this is the blockchain, very simple. There's many other information that is stored in single block, but pretty much this is the core information. Each block has a list of transactions that are stored in something called Merkle tree. The other thing that each block has is a hash of the previous block. That's how the chain is actually created, and that is how the blockchain is kept secure. And of course it has the main header, that is the hash of the entire block. So when we talk about blockchain, there are two operations that we can perform, and the first operation is very easy, very simple. It is the read operation. It is free. There are no limits reading for the blockchain. There are no limits verifying that data. There are no limits to check if the data is corrupted, and pretty much this is because of the blockchain being publicly distributed. Everyone can go and download, everyone can join the blockchain network. So this is probably one of the few things that we have no problems with in the blockchain. However, the second operation is a bit more tricky. It is the write operation, and there are many problems and limits with this operation. Sorry. We are probably going to be talking a lot more for the problems that are with the write operation. So if you are using blockchain, you might have heard of the word transaction. So what is transaction? Well, transaction is actually this operation that tries to change the data, the state of data in the blockchain. And the keyword here is tries. That is because there are many validations that are performed before the data is stored in the blockchain, and these validations are performed by the nodes. Such validations can be like checking if you have the amount that you want to send, or if you haven't spent the amount that you want to send, and there are many others. And this is pretty much where the problems comes. That's because majority of the nodes need to reach an agreement before writing the data, and this is very, very hard process in fully decentralized networks. And this is done currently with something called a consensus. There are many consensus algorithms out there, with the most popular being the proof of work. Basically, the proof of work requires you to provide something that is very, very expensive to produce and very hard for you to be able to create a block. And that's where the miners come, if you have heard for miners. That is pretty much how deep we are going to go for now on how the blockchain works. And here are the first set of solutions of problems. So when we talk about blockchain scalability, there are a few metrics that we can use to track these problems. The first metric that we are going to be using tonight is the transactions throughput, or the maximum rate of which the system can write transactions to the blockchain. The second metric will be transactions latency, or the time it takes actually for the transaction to be recorded in the blockchain. The third metric will be transaction fees, and the last metric, but not last of importance, is the data storage. as the network is immutable, it only grows bigger, and it's really hard to store the data and keep it running fully decentralized. So the first set of issues, first metric that we are going to check again, it's transaction throughput. So what is actually transaction throughput? Basically, you probably have heard of the sentence transactions per second, and that's how the transaction throughput is measured. And these transactions per second are calculated by something called block size and block internal time interval. I will talk about the block time a bit later tonight, but here I can say a few words for the block size. Basically, in the first slide where I briefly explained what the blockchain is, I said that there are a list of transactions that are stored in each block. And what I didn't say back then is that there are limits, and you can't just include 1 million transactions. So this limit is measured by different ways in different networks. For instance, in Bitcoin, this is measured by pure size, and the limit in the Bitcoin is 1 megabyte of data, while in the Ethereum it is measured by something called gas, and the gas is used for other things as well, such as powering the smart contracts execution costs that we are going to cover later again. So what are these numbers looking in different networks? For instance, Bitcoin can handle up to 7 transactions per second, Ethereum can handle up to 20 transactions per second, Litecoin can handle 56 transactions per second, Bitcoin Cash can handle 60 transactions per second, and Ripple can handle 1,500 transactions per second. The first thing that you might notice is that every single of the first 4 networks are using the POW or proof of work algorithm, and this is a key here. And the last network is using something called RPCA. I'm not going to go into much details of what this is, but pretty much Ripple isn't fully decentralized, and Ripple is semi-decentralized. That's why they're able to handle that many transactions, while the first 4 networks are fully decentralized. And I decided to put Ripple here only just to show you that how we can increase very easy the transactions throughput of different networks by just sacrificing the decentralization part. So when we talk about solutions later, we are looking for solutions that doesn't affect the decentralization and that are fully decentralized. So you might, this number might not tell you anything if you're not familiar, but pretty much again, what was transaction? Transaction was operation that tries to change the state of data, and you can view it as update query in normal databases. So pretty much, if we imagine having a fully decentralized messenger and messaging system, only 7 people, in case of Bitcoin, only 7 people will be able to send a message every second, and this is pretty low compared to what it needs to be. So let's continue. Where do we need to go? Usually when people compare the transactions throughput, they compare it to the Visa, and Visa can handle around 56 transactions per second, and even I'm not sure that this number is actually correct. That's because everybody and everywhere you can see this number being different, and it is purely because Visa has never actually handled more than 3,000 transactions per second, and that is because they don't have such load, and pretty much they just say that they can handle many more than that. And when people compare the transactions throughput to Visa, I think that it isn't good. It isn't good to compare the blockchain to Visa, and there are many reasons for that. First off, Visa handles that many transactions per second with very expensive fees. The fee for transferring money in Visa is around 25 cents, and this is very expensive. Again, if you have decentralized messaging system, it will cost us 25 cents for just sending a message, and even mobile operators today do it a lot cheaper. The other reason is that we actually need a bigger throughput than this, and there are many proofs of that. For instance, Twitter had 143,000 tweets in a single second in August 2030. I know that the idea of blockchain isn't to be a social media like Twitter. But again, if we want to change the world, we actually need to have the ability to offer the blockchain to a lot more people than actually Twitter does. So in reality, we need this number to be very big. So Visa is just an improvement. It is not the solution, and we need a lot higher transactions per second. And basically, you can now compare the previous numbers that were very, very low to what we actually need. And there's a huge way to go to there. So the second metric was the transaction latency. Basically, what transaction latency is? The time that the time that is needed for the block to be mined or created, or basically the time that miners need to provide the work. And this transaction latency is very important for many reasons. And the main reason is that it reduces the possibility of forks. I hope everybody here knows what fork is. Anybody who knows forks? No one? Okay. So the network basically can split in two halves. I will draw very simple in just a second to show you. But let's first see what these times look. So average Bitcoin has block every 9 to 10 minutes. In Ethereum, in a Litecoin, new block every 2.5 minutes, and Ethereum has new block every 10 to 50 seconds. And again, probably these times doesn't mean anything to you, and they're pretty slow. One reason for that is that the actual transactions are not executed every second. Basically, in the previous metric, we were just using transactions per second for measurement, but actually transactions executed when the block is created. So in Bitcoin, it will take 10 minutes for your transaction to happen. And in reality, this period is even higher. And it is higher because there is confirmation period that everybody in the network is using. Currently, people have agreed that 6 blocks is something safe. So actually, in reality, if you want to consider your transaction permanent in the blockchain, you want to wait for 6 more blocks. So for Bitcoin, it will look like 1 hour wait time. And that's again because of the forks. Basically, what fork is, so if you have the network here, like it is the blocks, okay, what can happen is that it takes some time for every single node in the network to hear about transaction, about new block. So what might happen is that somebody can build a block here, basically, and someone that has not heard of this block can create another block that is here. So the network splits in two halves, and if your transaction happens in this side of the chain, the bottom side, and it might not be permanent, and that's because at some point the blockchain will select which of the paths is the right one. So for instance, if somebody finds a block here, the upper part will have more work. It will be the longest chain. So actually the main network will be this thing like here, like this. So actually your transaction would never happen. It will be like you did nothing. So when you receive money, you need to be aware of this. Somebody can send you money, then in 2 blocks it might never happen, and 20 minutes is big time to wait to see if this is true. And again, the safe period is considered being 6 blocks. So where do we need this latency to be? Basically here the full solution will be milliseconds, and that's because how we are used to. But in reality, probably we are far away from this happening, and we can just accept something like 2 seconds or 1 second or whatever. So let's check dollar metric. Dollar metric is transaction fees, and fees are necessary currently. And again, this is because of the consensus, and that providing proof of work is very, very expensive. So the miners spend a lot of money, a lot of power to provide work. So basically your fee goes to them. So you can decide what fee you want to give to the miner. You can decide to give no fee. You can decide to give $1 million, whatever you choose. The actual difference between you giving a higher fee or lower will be the chance of your transaction being included in the block. And that's because, again, of the block limit. So if the block can handle for, let's say, only 100 transactions and there are 500 transactions waiting, when the block is created, the miner can choose only 100 to include in the block. So basically he will go and select the transactions that offer him the most money, and pretty much the others will be left waiting for next block, and so on and so on. It is a bit more complicated, but it is the simplest explanation. So what are the average fees in these networks? For example, when I created the presentation, the Bitcoin had around $1.50 for a single transaction, while Ethereum had something like half a dollar. And these fees are not set in stone again. This is pretty much how much people went to offer. So they can drastically change in a period of 1 hour. So if there's a big movement in the network, these fees can skyrocket. For example, the most expensive fees were in the Bitcoin around $50–55 in December 2017. Many companies back then decided to stop offering Bitcoin payment to in their service. For example, Wolf, that owns Steam, decided to not longer support buying games with Bitcoin, and that's purely because it was more expensive to actually pay the fee than the actual game. And in Ethereum, these fees were around $4 in January 2020, and Ethereum is a bit different, and that's because these fees are actually that includes actually the smart contracts execution, and smart contracts can affect the main network. This is a big issue that we are going to talk later, but pretty much there was a game called CryptoKitties that was 40% of the entire network, the entire network's load, and if a single smart contract that is a fully payable game can affect the network in this way, you can imagine what can happen if we really want to change the world. It is not really a possibility. So here, I don't know if you can see, is a chart from July 2017 till nowadays about showing the average fees. And in blue, you can see it is the Bitcoin network's fees, and on the bottom side down, you can see that is the Ethereum fees. So this is pretty much about fees. And the last metric that we are going to talk about is storing data. It is not last of importance again, but it just landed here. So all the information is currently being stored in every single node. So saving something in the blockchain is actually spread in, let's say, 50,000 computers, and this isn't really very good. And there needs to be a solution that changes that. For instance, the data sizes are here. First, they might look very bigger, but this is the full size of the network, including history changes, state changes, transaction histories, everything that you may store in the network. And for you to run a node, you can actually do it with less size than this, and this is still very big number. Again, the idea is that the network is fully decentralized, so everyone in the world should be able to run a node. And currently, if you need to give 100 gigabytes of space for you to store the data, it is very much for normal people. So again, this having huge data leads to centralization, and that's because not everybody will be able to run a node. You need to know that this only grows bigger, so it might end being 1 terabyte in 5 years, and then even some of the normal people, more of the normal people won't be able to run node. So again, it leads to centralization. So let's talk now about proposed solutions. first off, I want to say that when we talk about solutions, we actually talk about full solutions. We talk for solutions that actually either improve one of the metrics and don't affect the other metrics at all, or they improve the whole picture. Again, we can't really afford to affect the metrics in a bad way, so we can just improve. So the first solution that we are going to be talking about is the whitening network, and it is the Bitcoin's solution. So what is whitening network? Whitening network is pretty much an off-chain approach. It is often referred as the second layer in the Bitcoin system, and the idea is that your transactions won't actually go through the main network, and will go in off-chain. So how is this done and achieved? Basically, this is achieved with using something called payment channels that use multi-signature address, and I can't really explain you how this works without drawing, so I will get here and draw you a picture. So before starting drawing, I want to tell some story. So for instance, everybody probably here has a favorite bar or favorite shop or whatever that he might visit every day. So let's say I have a favorite bar. I will put it on this side here, and this is me. Okay, so in reality, I visit this bar every day, or maybe every next day, and I want to go there and drink 1 beer or 2 beers, and I want to pay with Bitcoin. So now, if I want to pay with Bitcoin, this transaction needs to go through the main chain. The miners need to provide the work, and again, the work is very expensive. So pretty much we are loading the main chain with information that we don't really want to load it, as the blockchain isn't here to do stuff like getting in consensus if I have paid $1 for a beer or I didn't pay it. So the idea is that if I know that I will have many relations with the bar, I can create and open a payment channel between me and the bar. So how this is done is basically we both agree that we want to create the channel, and we both deposit some Bitcoin value. So for instance, I will deposit 5 Bitcoins, the bar will deposit 0, and yeah, this is possible. There's no need for both parties to actually give a value greater than 0. So when we do that, there's something called that is multi-signature address here, and pretty much the money are stored in the multi-signature address. They are stored in terms of sheet that basically says that I have paid Bitcoins and paid 5 Bitcoins and the bar has 0 Bitcoins. When this happens, the channel is actually opened, and while the channel is opened, we can now start transferring money with each other without any limitations. So again, there are no limitations of how many transactions there are, no limitations of how often the transactions will happen between us. They are not executed by the main chain, they are only happening here, and how they happen is basically with that sheet that we stored in the multi-signature address. Basically, when I buy a beer, I get the sheet and I write that now I have 4 Bitcoins and the bar has 1 Bitcoin. We both sign the sheet, we both have a copy of the sheet, so we store that. Then I go to the bar again, I buy a beer again. Now we write on the sheet that I have 3 Bitcoins and the bar has 2. So this pretty much done every time. We can the bar can give me money as well. And when we went to cancel and close this channel, basically what happens is that the one of the parties, it is not required for the both parties to actually do this. Only one needs to go and basically provides the most recent sheet to the multi-signature address. The multi-signature address validates that the sheet is signed by the both parties. It validates that it is the most recent sheet, and when this happens, he basically closes the channel and distributes the money how are they described in the sheet. And there's something else that you need to know about this approach, and that is if a third party comes in a play. So let's say I have a business partner here. We are doing business for a long time, so we have a channel open between us. So one day I decide that I don't want to go to the office to actually do business, and I tell him that we should go to the bar. So we are going to the bar, we drink beer, do business, whatever. And my friend my business partner wants to pay the actual bill. Then he doesn't actually need to have a channel that is open to the bar. He can use the channels that are between me and me in the bar. So basically what will happen is that he will give me the money and I will give from my money to the bar. So he doesn't need to open a channel to the bar. And this is possible only if I have the money to cover the bill. So for example, if I have 3 Bitcoins only left and the bill is 10, I cannot really afford that, so it won't be possible. But there's actually a system that checks for such paths, that finds the shortest path and does it automatically. Okay, this is pretty much what the Lightning Network is. There are some slides, but I covered them pretty much with the talk, hopefully. So no transaction limit in the channel. You can do as many transactions as you want. The payment channels can be closed at any time by any of the parties. The main channel then distributes the coins after the channel is closed, and you don't need a direct channel with everyone that you might want to send coins to. So what are the benefits? Again, it reduces the load on the main channel. These small transactions are not longer executed by the main channel. They're happening only between us in the payment channel. So it only requires 2 transactions for that will happen on the main channel. 1 transaction will happen when the channel is actually opened, and 1 transaction to call the channel. So basically you're paying fees only 2 times, when you create the channel and when you close it. And the one good benefit is that it's already live on the Bitcoin mainnet. It is still on the beta, in beta, so there's many limitations of how many channels can be opened and how much money you can actually store in each channel. So sharding. Sharding is the Ethereum approach of solution. Sharding is very, very hard to describe without any technical details. So I'm going to be drawing again a very simple picture here, but pretty much we are familiar with sharding already. It exists in the traditional databases, so it isn't something new, but it's very hard to be developed in blockchain. So what is the idea about sharding is to split the network into shards. So again, I will come and draw here. Currently, if we have, let's say, 3 regions here, so this is NA, this is U, let's say Asia. So currently, every single region has some nodes, whatever number it is. Okay, so currently when a transaction happens, every single node in the world needs to actually come to an agreement, needs to process the transaction, need to make the validations, and this is very hard. First, because of latency, every node again needs to hear about the new block, every node needs to come to an agreement. And the idea is that there's no such need to actually have every single node process every single transaction. Again, this is really so for 2 reasons. Okay, whatever. So the idea is that sharding will split these regions basically in shards, how I draw them. Or this is very simple. It won't be like region-wise or whatever, just for the example here. So you can consider each of these regions being a shard. So when a transaction happens in Europe, it will be only processed by the nodes that in Europe. And when transaction happens in NA, it will be processed only by the nodes in NA. So the difficulty here, so there's no actually need for it to be, let's say, one big shard in Europe or Asia or whatever, there might be 1,000 shards in Europe, 1,000 shards in North America. This number can change depending of the world and whatever. And the difficulty here is that what happens when a transaction is made between, let's say, NA and Asia. There needs to be a protocol that pretty much talks between networks, and this is pretty much the hard part about doing sharding. And I don't want to go into too much technical details, so that's pretty much how much I'm going to explain sharding. So transactions are not processed by every single node, and the idea is that currently when you add a new node to the network, it actually decreases the performance, and that's because there is one more node that needs to come to an agreement, one more node that needs to hear for every single block. So the idea is with sharding is that when you increase the number of nodes, we can increase the number of shards, so it will actually increase the performance of the network, and every time you add a new nodes, it will actually increase the performance. So we as customers and developers, we don't need to worry about this. The idea is that Ethereum developers will basically create an interface that works on the back end and pretty much provides us with the same things that we have nowadays. So we actually interacting with smart contracts won't change for us. It will change on the Ethereum backend, and developing the apps won't change for developers as well. So the challenges of the sharding is that it is not possible to do with proof of work. That is because one shard can be overtaken with proof of work, and the network needs to change first to proof of stake, and Ethereum has such plans. So proof of stake is basically, instead of providing work, you have some huge amount of money that is stored. When you deposit this money, you're given the rights to validate transactions, and each time you validate transaction, you get some of the fees for you. And if you want to cheat the system and why, your money will be pretty much taken from you, so you're going to lose your entire deposit. So the other challenge again is the cross-shard communication. It is currently being worked on, and again, sharding is probably far away from being live, but it is a very promising solution. So there are many other possible solutions, but we won't have the time to cover each one of them. So one of these possible solutions is Raiden. Raiden is similar to Bitcoin Lightning Network. It is again an Ethereum solution, and the key difference is that Raiden actually supports every single ERC20 token, so you can create payment channels with tokens, not only with the main currency that is Ether. Other possible solution is altcoins, basically making different coins and sidechains for different purposes, off-chain computation, and directed acyclic graph. There are many other possible solutions, but again, we won't have the time to cover them all. So pretty much this is about the first part of scalability problems and solutions. So do you have any questions about this first part? Let me check.
Do you think sharding would
Just some for. Sorry, what?
Do you think sharding would actually solve the throughput problems in Ethereum right now, and to what extent?
So the question is, do I think that the sharding will change that the sharding will improve the transactions throughput, and in how extent? Yeah, the plan is that it should increase the throughput. Currently, there's something bad, and the idea is that for a contract to interact between shards, it will need for two transactions to happen because it's between shards, and this is currently, I think, being worked on and improved. So the idea is that the sharding will improve the smart contracts interaction. Yeah.
Do they have some expectations to what would be the numbers in terms of transactions per second expected when this is?
No, I don't think so. Sharding is again too far away. I personally think that it's not even start developing. It is only on paper. with their architects doing the things, and they're pretty much looking for developers to recreate it. Other questions? So there are no questions, let's leave. Okay. So smart contracts. First, again, I hope everybody knows what smart contracts are. So there are few networks that actually support smart contracts currently, with the big one being the Ethereum network. It supports smart contracts with Solidity. You probably have heard of it. The other network that supports smart contracts currently and it's very promising is Neo. It supports multiple languages, C#, Java, Python, and they plan to support many more languages, but currently they support this, I think. And Neo has a bit of different approach of how the fees of smart contracts execution are paid, and I will go into more details in just a minute. And there are some other networks that are going to be supporting smart contracts that are interesting, and one of these projects is EOS. It supports again multiple languages. The other project being RSK. So RSK is promised to support smart contracts on the Bitcoin network. It will do so with sidechain basically, and these two are still being in development. I think EOS has a beta, I'm not sure. So we are not really going to talk about them in the next slides, and we are going to focus mainly on Ethereum as it is the biggest one. And there's private networks that actually run smart contracts as well. For instance, Hyperledger Fabric can run chain code in private blockchains for companies. That is the first time that I mentioned private blockchains, and that is the idea here isn't to talk about them. So what are the issues with the smart contracts? First, previous issue apply. That's purely done because, again, invoking a method or a function or whatever in a smart contract is actually a transaction that is executed on the main chain. So pretty much everything that affects the transactions affects the smart contracts interaction. Security is a huge issue. There are a lot of money that are being stolen in the past. Immutability is an issue as well. It might sound weird for some of you, but it is actually a problem. We are going to go deeper into these first three in just a second, but I want to say that actually writing smart contracts bug-free is very, very hard and very difficult, as the contracts are running on the version that they are deployed on. So actually improving the Ethereum version actually doesn't improve the version of your contract running, and it requires different approach when developing. So for instance, senior developers that are developing a normal programming code might run in some issues and some bad habits. So they need to be very careful when developing smart contracts. So previous issue apply. Let's go again into the 4 metrics, but this time for smart contracts. So transaction throughput, the transaction throughput per second limits applies to the actions of the entire network. So pretty much the transaction throughput applies for smart contracts, and it is vice versa. So actually again, if we have a huge smart contract that is very popular, it will actually make the people that are just using the network for money transfers actually suffer, and this is pretty huge problem. And actually there is things that are being worked on to actually improve this, and there are solutions that are planned. So transaction latency, here it is even a bigger problem as the data is not modified in real time. So you might run something like decentralized auction, and the bidding can be very weird just because the transactions are not executed in the real time. Transactions fees, well, in Ethereum, smart contracts execution costs money. Again, that's why that is the reason why Ethereum has limit limits in form of gas and not in form of box size. So that's how the fees are affected. You basically pay with gas. The gas has a price that is currently in Ether, and pretty much you give a limit, so you can limit how much gas the contract that you're invoking can spend. And this is a problem, as you are not possible to have a good business logic in the contract, as it will require bigger expenses for the user that is invoking the contract. So in reality, you cannot have any business logic, and you should reduce it in your contract. And New has a cheaper approach. New has cheaper execution cost. That's because New has pretty much two currencies. One is the main currency that is New itself, and the other currency is being the gas. So the gas in New is actually currency. It is being generated over time. That's how it's kept very cheap. It is being generated with extreme rates, and it is generated by you having a New. So for instance, if I have 1000 New in my account and they just stay there, I don't do anything with them, they're in my wallet, I will be getting gas generated let's say every day. So the gas that I receive, I can either use to invoke different contracts and pay for their execution, or I can sell it for other people. Yeah. In Ethereum or on New or on Bitcoin? Bitcoin doesn't have smart contracts yet, so there's no actually fees. But in Ethereum, the price is measured by the gas price. There are actually websites that you can go and check what the current gas price is, but it's changing constantly. It is measured in Gwei, I think, so you can pretty much go and check it. I will show you after the presentation. Okay, so pretty much that's for New and transaction fees. And storing big data isn't really a possibility. So you shouldn't be storing huge data in your contract. Again, storing data actually costs money again. So every single big data should be stored in distributed storages such as Swarm, Storage, and APFS. And I have used APFS many times, so it's very easy. And if you are a developer and you haven't used any of these, please go check them. They're very helpful. So security. There are many security issues with smart contracts that are publicly known, and there are many hacks that have happened in the past with many of these security issues. There are even a good and big percentage of the smart contracts that currently run, they all have security issues, and this is known by everybody. So one of these security issues is so-called Trailer attack. It was used in the DAO hack. 3.5 million Ether was stolen. It was $70 million back then. Now it is close to $2 billion. So you can imagine the scale of this. The other thing is security thing is underflow and overflow. Actually, integers can overflow and underflow in the contracts, and many of the contracts that are running nowadays don't have any checks for such behavior. There are attacks is denial of service attacks that basically stop your code from execution. Or attacks are short address. I'm not going to go later into much details about this, but basically if your address is ending with trailing zeros, because the entire information is stored with bytecode and you have trailing zeros, you can pretty much shift the entire data with 1 bit, and it might produce weird behavior of you receiving more money than actually you want to receive. Other issue is transaction ordering. Basically, again, the miners decide which transaction will be included in a block. So you shouldn't really have any logic that relies on the order of transactions as there's no such thing, and the miner can always reorder things when including in the block. Last thing about security here is timestamp dependencies. So you really shouldn't have any logic in your contract that actually has timestamp dependencies. So that's because, again, the miner can control when the block will be created by some extent, so they can manipulate the time of the creation of the block. So if you have something like random generated in your contract that takes the timestamp and generates a random number, it won't be actually a random number, and it will be deterministic one. So let's look at some code about these first 4 issues. We are going to go into some details. I hope most people here know about programming and code. So reentrancy attacks, I'm going to talk how it happened, but first, how many of you know about the reentrancy attack at all? Okay, so basically every single contract, this is a very simple contract. What this contract does is it has a variable that basically is a counter. It stores an integer for a counter, and it has a function. So the thing that you need to know here is that this function is actually an anonymous function. It doesn't have name. So what this means is that every time this contract is being executed with any invalid or not existing method, it will actually go and execute this function. Or anytime that the contract receives money without giving any data, this function will be executed again. So for instance, if I go and I have a code, and I have a code, let's say demo do something, okay, whatever. So there's no such function that exists in my code. So what will happen is that this anonymous function will be executed if somebody comes and gives me 10 ether because and he does that without giving me any data or invoking any function that exists in my contract. Again, this function will be executed. So in the current contract, because I have no functions, basically anything that is invoked will actually increase the counter, and every time the anonymous function will be executed. So this is very important that you need to know for us to actually for me to actually explain you how the actual attack happened. So let's go to the actual attack. First off, this is the contract that pretty much let's say it's a token that you might know. It stores here basically stores the user balances. It uses the user address or wallet and actually stores the amount of how many coins they have, let's say that. And there's a function that what it does is withdraws the balance. So if I deposit 10 ether, I can call withdraw balance, it will return me 10 ether. Very simple, very straightforward. And what happens in this function is first the amount to withdraw is saved in variable, and there's require. Requiring smart contracts is pretty much an if, that if it fails, if the statement inside fails, it will actually revert the entire thing back in like it never happened. So in smart contracts there is something called revert, and if you have a logic, let's say it's 100 lines, it can execute to the 99 line, and if the 99 line says revert, it will actually revert everything like it never happened. So pretty much if you received money or anything, it will be reverted back. So pretty much this line says that I will go and give the money to the invoker. So for instance, if I want to withdraw my money, I will give the money to this person, and if this fails, if I am not able to actually give the money, just stop here and revert. And only when this is true, actually the user balance will be reduced to 0. So for programmers, probably there's no anything weird here, but what the hacker used is the anonymous function of the previous example. So actually the message sender can be the other contract. So what the hacker had is this anonymous function, and pretty much this anonymous function was basically just going to the main contract. the main contract and just executing withdraw balance. So in reality, what happened is that this function here, so this function here gave money because the hacker had no other functions and had an anonymous function. This anonymous function was executed, and the hacker stated that it went to execute the withdraw balance again. So what happened is that this line executed the withdraw balance again, and again we are only here. So actually we have never reduced the balance of the user to 0. So this becomes a recursive, so the hacker can drain the entire value of the main contract. And here is something again that you need to notice, that the hacker is very smart, and that is that he has this if statement here that basically checks the balance of the main contract and checks if this balance is still greater than the money that he wants to steal. And that is again because if the main contract doesn't have an out balance, it will just fail here, and what will happen is that it will revert, and again reverting will revert back to the previous state. So this might have happened 1 million times of him draining 10 ether, and if it fails at the end, it will basically revert everything and he would have never stolen anything. So he's very smart with that. There's other things that you need to know, and that is again that it costs gas to execute, so it cannot really run forever. Non-smart contract code can run forever, and that is because of the gas limitation of when the code is executed. So to be safe, use either a .send or .transfer when you're transferring money to somebody. The next issue will be underflow and overflow. Pretty much again, this is very straightforward function here that can be in a contract, and what it does is basically transfer money from my address to some address with amount, and it then checks if I have the balance. It is very normal, very easy to understand. Then what it does is first it reduces my balance, and then it increases the balance of the person that is receiving money. The problem is that actually this is never checked what value will be. So if the receiver has a lot of money or he is given a lot of money, his value that is stored can overflow, and basically it will be not what is expected. So to check this, there's a very easy solution here, and that is when you check for the sender balance. You can actually do this check, that it basically checks that receiver current money plus the value that is being received is actually more of his current money. So very easy and very straightforward, but many contracts don't do this nowadays, and they might run in problems in the future. Again, this is unsigned integer 256. This is very big number. It is hard to overflow, but this can happen. So the next attacks that we are going to see is the denial of service attacks. Pretty much they can there is possibility, if you haven't written your code correctly, to actually for the hacker to actually deny the service of your contract. For instance, here's very simple action contract, and what it does, it stores the current leader and it stores the highest bid, of course. So it basically keeps track of who is the highest bidder. And there's a simple function that what it does is it bids on the item. So let's say I have started an action with car, I have bid 1 ether for it, and somebody can come and call the bid and send let's say 2 ether. So first it checks if the given amount is more than the highest bid. So if you're giving me 1 ether for bid and I have bid 2, it won't happen. The second thing that it does, it sends the money back to the current leader. So if you outbid me, the contract will give my 1 ether back, and after that it sets the new leader and the newest highest bid. The problem here is that, again, this can be manipulated because of the anonymous function. So for instance, I can have anonymous function that pretty much reverts, and again, reverting will revert the entire state. So I can make that this one will never go, never be true. I will never be able to actually receive the one ether that the contract is trying to return me. So pretty much I will win the car with 1 ether, and nobody in the world will be able to outbid me. And this is very, things that people need to be careful. There are many other denial of service examples that we can show, but we don't have that much time. So pretty much this is about security. Now a few words about immutability. So the data is immutable again. This can be potentially be very bad. In my opinion, and this again, it's my opinion, is that we actually don't know how to handle immutable data. And in reality, such data doesn't exist for a reason. For instance, currently, if somebody, let's say, uploads something bad like child abuse or something like that, we have no way to delete it. It is there forever. So we need to be careful with that. We need to be very, very careful with that. And yeah, pretty much that is. And the other problem with immutability is that your code is immutable as well. So it cannot be controlled. There are pluses and minuses when we talk about controlling the code. First off, it cannot be controlled by any legal authority. So this might be a plus for you or whatever you're doing. Or like when people create the tokens, it cannot be controlled by anyone. The minus is that actually it cannot be controlled by you. So in reality, no one can control your code, and it is really hard to maintain. Having a bug is really painful, and pretty much either you need to have left doors for you to upgrade the contract, or you need to basically create a new contract. So this is pretty much about smart contracts. Now we are going to go to the future, but first, do you have questions about smart contracts? Let me check again. So okay. Do Ethereum plan to support smart contracts with other languages, not only Solidity? Are you Solidity smart contracts used on other blockchains? So Ethereum has planned to support smart contracts with other languages. Basically, the code that is actually executed in the Ethereum virtual machine isn't actually a Solidity code. The Solidity code is compiled to bytecodes, and pretty much the bytecodes are stored. So anyone can basically create a language whatever they want, and pretty much they just need to compile the code to the right scheme to work in the Ethereum virtual machine. And I think colleagues have given me recently information about that there are actually other languages that are coming. And I don't know if there are other blockchains that actually run smart contracts with Solidity, but there might be, I don't know. So, questions here? Okay, now let's get into the train and get into the future. First off, I want to say that in this future, everything that we have spoken till now is solved. In this future, we have no problems. Blockchain is perfect, and pretty much here we will probably only be asking questions than actually talking about solutions. So the first problem is the quantum computing threat, and quantum computers actually exist today, and they are very, very limited, but actually exist, and they will only improve. So how safe is actually blockchain from something like quantum computers? Actually, I cannot really answer this question. There are many opinions. Some people say that it is safe. Some people say that it is not safe. Actually, this is a cryptographic question, and there needs to be a cryptographic people to actually answer this question. But in reality, it doesn't matter if we are safer from quantum computing now or in 5 years. Actually, if we want to change the world and the blockchain is here to stay, we might face this problem in 10 years, or we might face it in 20 years, as the computers will only improve with time. So we need people that are actually paying attention to this problem closely at all times, and they're actually developing solutions for these problems. And there are actually people that already are doing this. This is pretty much few of the solutions that offer different cryptography. I cannot even pronounce this, so I just leave them here if somebody wants to actually go and check them out. But pretty much they have issues as well currently as they are being developed, but there are very, very smart people that are actually working on such solution. The other problem is what I call normal people problem. I don't know, maybe there is a word about this, but that's how I called it. Basically, if the blockchain is perfect and we are changing the world, how do we introduce the blockchain to the normal users, to the daily people? Currently, your identity or your wallet is secured with private keys, and private keys are very hard to actually keep secure and to actually keep private at all, and they're even hard for developers. So how do we make the actual normal people secure their key? So one of the solutions is actually to make again a user and password and to store the key in your website. But how many of you would actually store somebody's key on their site? Is there anybody? Okay, that's good. So yeah, in reality, you shouldn't be actually storing any private keys on your website. That's because it automatically puts a target on your back. Every hacker will try to hack you because it will steal the money of the people, and so on and so on. So even if you do so, 25%, this is a real stats that I have gathered, 25% of the people actually forget their passwords in daily basis. So 5% of these people cannot even remember a single password, even that usually these passwords are very, very simple. They're very easy. So how do we make them keep their private keys? How do we store them so the private key is kept safe? And maybe some of you think about hardware wallets, and they are actually not a solution. Again, people whose stuff, around 10 million keys are lost every year, around 5 million wallets are lost every year. There are many ID cards that are lost every year, many Visa cards and whatever. And the main thing that you need to know here is that everything that I mentioned that people are using today is actually recoverable. So you can recover your ID, you can recover your keys, you can recover your wallets, but in reality you cannot recover your private key in the blockchain. So if you use your private key, it's gone forever, you cannot recover it. And actually there are many people that are getting very angry, they cry, and this isn't something that I'm making up. There are a lot of stats for it, and there is actually a name, but I forgot it. So they cry about forgetting their password that is recoverable, and actually probably their passwords don't even store money or any value than, let's say, pictures or a friend contacts or whatever. So again, how do we make the people actually store their private key in secure way? I don't really have an answer for that, but if the blockchain advances and wants to change the world, there must be an answer for this type of questions. The other thing is cross-platform development. So every developer here has been there probably. So cross-platform development is very, very hard. For instance, having much platforms like cross-browser development, mobile development a few years ago, you needed to care for many different displays, many different phones, and even today it is really worse. Developing games like for Windows, PlayStation, Xbox, and mobile, it's very hard again. And this issue is presented for network not communicating. So if we have, let's say, 20 networks that support smart contracts, developing your business, showing your business and having your business on each of these networks, it will be very extreme and extremely hard. So we really need to do something about this. And there's something else that makes this case even worse, and that is because the actual contract data lives only on the network that the contract is. So if we go back and let's say we have issues with cross-browser development, it is basically just fixing the screen on different browsers, but your database is the same, your backend is the same, so it's very easy. But here our contract data will be different, so basically our database will be different on each network, and this will be very, very painful. So we need to find a way for either the networks to communicate with each other, or we need to find a standard for smart contracts, so you will be able to run your contract in 20 different networks without actually doing extra work for each of them or changing your code. So lastly, let's not recreate this issue again, please. And this is pretty much for the talk. So do you have any questions about the entire talk or the last part of the future? Okay, let me check the Slido first. So what about when in the middle attack? Yeah, there are many different attacks, but actually I really cannot talk about every single attack, and this is just time. And pretty much if we go to do a real talk that goes deep into technical levels, pretty much there can be entire talk for Lightning Network, there can be entire talk for sharding, entire talk for smart contracts security, and each of these issues can be viewed as just only one talk and can be dived a lot deeper. I decided to tell for different issues with just a little bit. Do you have Bitcoin or other cryptocurrency? I don't want to share this, so I don't know. Why should I use smart contracts if they are not immutable? Well, yeah, this is a good question as well. That's why I said that it is weird. In some cases it can be a problem, in some cases it can be plus. So again, I don't really have an answer. It depends on what you want to use the contracts, but what I meant by immutability problems is that we actually need to be very careful of what we store there, and this is pretty much where the issue is, that we should be able to actually have a way to know what we are storing more in depth, or I don't know how to say it. Here, anyone? Well, okay, this is pretty much everything, so thank you all for coming. I hope you all enjoyed it and to learn something new. And if somebody wants to stay for a beer after, yeah, okay.